All right, I wanted to work this fundamental problem to kind of go through the process with you. And what we have here is a 150-pound crate held up by 3 cables. And he gives us the endpoints of the cables. Again, rigid body dynamic, rigid body statics, which means that we're assuming these are straight lines, no sag. So we just want vectors from, say, A to B. So what I'm going to do is write down the points, A, B, C. Don't need to write D, I don't have a distance. So really all I'm going to have to do is worry about A, B, and AC in terms of the points here. He tells me the weight's 150, so I call it T 150. Then I'm going to write my position vectors. Here's my free body diagram. I've kind of here on top of it. You can see I'm going from A to B, A to C, A to D, and then my weight's down here. So what we're going to do, write our position vectors A to B, final minus initial. I have to do transpose in MathCAD. I'm using MathCAD here, which is the version I'm using of it is free from PTC. Google PTC or Google MathCAD, and you can get a free version of it. Now, the version I have just does basically arithmetic, but it does do vectors. It doesn't do the symbolics, doesn't do the algebra, but if you pay for it, then you can have it do the algebra too. And I think student version is right around $100, so it's not bad. Probably well worth the investment. But the free one is certainly, you can think of it as a mathematical data, like Word, only it does math. So anyway, A to B, I subtract B minus A, and let's see if it's right. So if I start at A, I go minus 6 in the X, I go 3 in the Y, and up 2 in the Z. A to C, I go minus 6, minus 2 in the Y, and up 3. So yeah, that looks good. Calculate the magnitude of those, 6 squared, 3 squared, 2 squared, square root. I get 7 for both. So I'm going to write my unit vectors, AB over the magnitude of AB. So what I went ahead and did, since I could do fractions, I went ahead and did it as fractions, sort of by hand, and plugged it in here. 6 over minus 6 over 7, 3 over 7, 2 over 7, and then put them into my UAB. So that's that. Same thing for UAC. Minus 6 over 7, minus 2 over 7, 3 over 7. So there's my UAC, AC over magnitude. Gives me that, a decimal. And that's my fractions. And then AD is all in the plus X direction. So I just made it 1, 0, 0. And then I'm going to use capital T for my vectors, little t for my magnitudes. And so the vector force TAB is magnitude times direction, magnitude times direction. My weight is just the weight in the negative direction. I call the vector W and the magnitude WT. And then AD is just TAD UAD. And so then I'll pull all of those, I'll get the X parts of all of them. So the X part, some of the forces in the X has to be 0. So that was minus 6 sevenths. 6 sevenths TAB minus 6 sevenths TAC, and then TAD is all in the X direction. So there's TAD right there. There's the vector. In the Y direction, all we really had was AB and AC. So 3 sevenths and a minus 2 sevenths. See, 3 sevenths and a minus 2 sevenths, and that one didn't have a Y part, and the weight don't have a Y part. And then the third one's the Z. So the Z part of this one is 2 sevenths. So 2 sevenths TAB, 3 sevenths TAC, and nothing for UAD, but we do have weight minus WT. Or all my symbols should be positive numbers if I draw my pictures right. If you want to do it in terms of unit vectors, you can do it there. But here, then I'm going to solve the second equation for TAC. And I'll end up dividing 3 sevenths over 2 sevenths. The sevenths cancel. And I'll substitute that into the third equation for TAC. And then I can factor out a 2b, and I've got 2 sevenths plus 9 14ths. Divide. You could do that as a single fraction. And I get TAB. And then I go back and use my formula for TAC. And then I go to equation 1. Now I know TAB and TAC, and I can find TAD. Solved it for that. And there's my numbers. Now to do a check, what I'm going to do is I'm going to put them all into their vectors. So TAB is TAB UAB. So it's that. TAC is TAC UAC. and TAD is TAD, UAD. So there's my 3 vectors, and then my weight, of course, which is 0, 0, minus 150. And MathCAD does vectors, so if I simply add those 4 forces, it should be 0, which it is, so that's a good check. Now, in terms of matrices, what I have to do is I have to write these equations in matrix form. So I put what I'll do is I'll make a vector T, which is TAB, TAC, TAD. So it'll be A times T. A is my coefficients. And if you look at the equations, what I did them here, the first column is all the X's, all the Y's, and all the Z's. The first row is all X's, all Y's, all Z's, and the columns are UAB, second column. So that's what I have here. So I load up my matrix, the unit vectors. It's those numbers. You can go compare. And then C is minus the W, because you bring it over to the other side in standard form. And then since A times T is C, then if you multiply from the left by A inverse A is I times T is T, and then you multiply both sides by A inverse, and so your answer is A inverse C. MathCAD calculates A inverse for us, so we calculate A inverse times C, and we get those numbers, and you'll see those numbers are the same ones we get up here. 161, 242, and 346. Okay, I've loaded up the PDF of that MathCAD file for you to look at. So you can sort of go over it in your own time, but that's the process. I've got a couple more work. I'll see you in the next video.